Hello everyone. Today we will see section 21 on the field of quotients of an integral domain. Now remember that an integral domain capital D is a commutative ring with a unity 1 not equal to 0 and containing no divisors of 0. From this figure you can see that the collection of all integral domains lies inside the intersection of commutative rings and rings with a unity, and the collection of all fields lies inside the collection of all integral domains. As an example, you can see that the set of integers under usual addition and multiplication forms an integral domain, and the set of non-negative integers less than p when p is a prime under addition modulo p and multiplication modulo p is an integral domain. In fact, it is a field. And the ring of polynomials in X with coefficients from Z. We denote it with Z of square bracket of X. Under polynomial addition and polynomial multiplication is an integral domain. Now you can see that there are commutative ring with unity 1 not equal to 0 which are not integral domains. That is, consider Z6 under addition modulo 6 and multiplication modulo 6. You can see that it is not an integral domain because it contains divisors of 0. For you can see that 2 and 3 are non-zero elements in Z6, but the product is 0 and hence they are divisors of 0. Now we already know that every field capital F is an integral domain, and also every finite integral domain is a field. Next, we are going to prove theorem 21.5, which says that any integral domain capital D can be enlarged or embedded in a field capital F such that every element of capital F can be expressed as a quotient of two elements of capital D. And we call such a field capital F as a field of quotients of capital D. Now it is well known that the field of quotients of the integral domain Z is the field Q of rational numbers. That is, any rational number is the quotient of two integers. For instance, you can see that minus 2 can be expressed as minus 2 over 1, and 0 as 0 over 1, 3 as 3 over 1, and so on. That is, any integer in Q can be expressed with the help of an ordered pair where its ordinates are 1. Now not only that, you can express any rational number with the help of an ordered pair as given in this example. So it is natural to take Z cross Z, that is the set of all ordered pairs AB where A, B are elements of Z to represent the elements of Q. But we can see that there cannot be an element in Q whose denominator is equal to 0. Hence, we modify our collection to S, which is equal to Z cross Z star, but Z star is the set of non-zero integers. So it becomes the collection of all AB where AB are elements of Z and B not equal to 0. Now this is not enough, for we can see that minus 2 over 1 is equal to 12 by 6, minus 12 by 6, but the corresponding ordered pairs are not equal. Similarly, you can see the equality of other rational numbers and the inequality of the corresponding ordered pairs. So what makes two rational numbers a over b and c over d equal? We can see that we just need AD equal to BC. So we introduce a new relation between the ordered pairs in S by AB and CD. The ordered pair AB and CD are related if and only if AD equal to BC. So you can see that tilde is an equivalence relation in this case because we know that AD equal to BC again implies A over B equal to C over D. Now once we know that the relation tilde under consideration is an equivalence relation, we can have equivalence classes so that all ordered pairs corresponding to equal rational numbers belong to the same equivalent class. Now we denote an equivalence class corresponding to an ordered pair AB with the square bracket of ordered pair AB, and let capital F be the collection of all equivalence classes of ordered pair AB in S. Now we can see that when two rational numbers are equal, the equivalent classes of corresponding ordered pairs are equal. Now it makes sense to identify the equivalent class of ordered pair AB with A over B, that is a quotient of the integers A and B. So once we have an analogous definition of the addition and multiplication in F, we can see that this capital F and capital Q are isomorphic. Now keeping all these observations on one side, let us go to our main problem. So let a capital D be an integral domain that we desire to enlarge to a field of quotients capital F. So we start with the capital S to be the collection D cross D star, that is the collection of all A, B such that A and B are elements of D where B is not equal to 0. Now we introduce a new relation tilde between the ordered pairs in S as in the previous case, defined by AB and CD are related if and only if AD equal to BC. Our first claim is that tilde is an equivalence relation, and we will be proving it in the very next slide. So in that way we define the elements of capital F, and after that we define the operations, the addition and multiplication in capital F. We then prove that capital F is a field under these operations and the integral domain capital D is contained in capital F. So once tilde is an equivalence relation, we define capital F to be the collection of all equivalence classes of ordered pair AB in S. Now from the previous observations, the equivalent class of ordered pair AB is viewed as the quotient of A and B, and hence the structure of operations between the elements of capital Q is applied in the new definitions. So we will revisit these operations once we prove or claim 1 that tilde is an equivalence relation, and then we prove that these operations are binary operations and they are well defined. So let us move to our first claim. So we start with the S, the collection of all ordered pairs AB with A and B are elements of the integral domain capital D with B not equal to 0, and two ordered pairs AB and CD are in relation tilde if AD equal to BC. We first start with the reflexive property. It follows very easily since we can see that AB and BA are the same since D is commutative. Similarly, in order to prove the symmetry property, let AB tilde CD, that is AD equal to BC. Then we can see that since D is commutative, we can rewrite this AD equal to BC to CB is equal to DA, and that is a requirement for CD and AB to be in the relation tilde. Now finally, to prove that tilde is transitive, we start with the AB tilde CD and CD tilde RS. That is, we have AD equal to BC and CS is equal to DR. We need to prove that the ordered pair AB and the ordered pair RS are in relation tilde, that is AB tilde RS. For we need AS is equal to BR. For that we start with ASD. So you can see that D is commutative and hence this is equal to SAD, and since AD equal to BC you can rewrite it to SBC, and since we have a relation with the CS, let us rearrange to make it BCS, and applying CS is equal to DR we have it as BDR. Now just to rearrange to get BRD, and since D is not equal to 0 and D is an integral domain, we have AST equal to BRD implies that AS equal to BR, which is the requirement for AB tilde RS. Hence we have completed our proof, and tilde is an equivalence relation. Now let us go back to the definition of the addition and multiplication in capital F, the collection of all equivalent classes of ordered pair AB in S. We need to prove that these operations are well defined. But before that, let us show that these operations take elements of capital F to capital F itself. For we have the equivalent class of ordered pair AB and the equivalent class of ordered pair CD are elements of F, implies that B and D are not equal to 0. Since capital D is an integral domain, we must have BD not equal to 0. Hence, we can see that the sum and product of the elements of capital F are again in capital F. Now, let us prove that these operations are well defined. For that, we start with the two elements from the corresponding equivalent classes. That is, let A1 B1 be an element of the equivalent class AB and C1 D1 be an element of the equivalent class CD. So we need to prove that the equivalent class of A1 B1 and equivalent class of C1 D1 gives a sum of the equivalent class of A1 D1 plus B1 C1 B1 D1, and that must be the same as the equivalent class of AD plus BC and BD. In order to prove this, it is enough to show that A1 D1 plus B1 C1 into BD is the same as B1 D1 into AD plus BC. So, since we have A1 B1 is an element of equivalent class AB, we have A1 B1 and AB are in relation tilde, which means that A1 B is equal to B1 A. Similarly, C1 D1 is an element of the equivalent class. CD implies that C1 D1 and CD are in relation tilde, which means that C1 D and D1 C are the same. Now, if I multiply the first equation with d1d on both sides and the both sides of the second equation with b1b, and if I call it the equation number 1 and equation number 2 and add them, we get a1b d1d plus c1d b1b is equal to b1a d1d plus d1c b1b. Now, since capital D is commutative, any rearrangement is possible within the terms, and hence if I take BD outside from the first two terms and B1 D1 outside from the last two terms, that is from the right hand side, you can see that the first two terms gives the required LHS and the second two terms gives the required RHS. Thus, we have proved that the addition is well defined. So, in order to prove that the multiplication is well defined, we need to start with the product of the equivalent classes of the ordered pair AB and ordered pair CD, and that must be the same as the product of equivalent classes of A1 B1 and C1 D1. So you can see that if you consider the equations 1 and 2, if you remove the post multiplied parts from both of these equations and just multiply, you can obtain the required conditions, and hence you can prove that these operations are well defined. Next, we will prove that under these well defined binary operations, the capital F is a field. So we need to prove all the field axioms. So for the first one, let us prove that capital F is commutative under this addition operation. So for that, you need to start with the sum of equivalent class of AB and CD and the sum of the equivalent class of CD and AB. You need to show that this AD plus BC BD, the equivalent class of AD plus BC BD is the same as the equivalent class of CB plus DA AB. So for that, you need to show that two ordered pairs are in relation tilde, and that follows directly from the commutative property and other axioms of the integral domain capital D. Similarly, you can prove that the addition is associative or any other property. For example, in order to prove that 0, 1, the equivalent class 0, 1 is an identity element of for the addition in F. So you start with the equivalent class of AB plus equivalent class of 0, 1, and by the definition it is A into 1 plus B into 0 comma B1 equivalent class, and which is the same as the equivalent class A plus 0 B, and which is equal to equivalent class AB. So we proved that the equivalent class 0, 1 is an identity element for addition in capital F. Similarly, we can prove that the equivalent class minus AB is an additive inverse for equivalent class AB in F, and other properties required to prove that capital F is a field under these operations. So it is not difficult, and you can try this and you can ask if there are any doubts regarding this. Now we need to prove that capital D is contained in this capital F. So that is next lemma. So the map I from D to F is given by I of A equal to equivalent class A1, that is an element A in D is taken to the element the equivalent class of ordered pair A1 in capital F, and we need to prove that this is an isomorphism with a subring of capital F. So in order to prove that this is an isomorphism, we need to prove that this capital I is a homomorphism and it is 1 1. We don't need to prove that it is an onto map, since we just need to show that this isomorphism is onto a subring of capital F. So for that we first prove that it is a homomorphism, that is we need ring homomorphism properties, that is I of A plus B is equal to I of A plus I of B, and I of AB equal to I of A into I of B. So in order to prove that it is a 1 1 map, you need to start with I of A equal to I of B and prove that A equal to B. So if I directly take you to the place where it appears in your textbook, so we have A and B are elements of capital D. We need to prove that the first property, that is I of A plus B is equal to I of A plus I of B. Now by definition, I of A plus B is A plus B 1, equivalent class of A plus B 1, where I of A plus I of B also takes you to the same equivalent class, and hence you have the first condition for the ring homomorphism is satisfied. Similarly, we can start with I of AB, which is by definition the equivalent class AB1, and I of A into I of B means equivalent class A1 into equivalent class B1, and by the definition of the product you will get it as the equivalent class AB1, and hence you can show that I is a homomorphism. Now it remains to show that I is a 1 1 map. For that you need to start with I of A is equal to I of B, that is we have equivalent class A1 is equal to equivalent class B1, that is the ordered pair A1 and B1 are in relation tilde, which gives you the condition of A into 1 equal to 1 into B, which means that A equal to B. Hence you started with I of A equal to I of B and reached at A equal to B, and hence we proved that it is a 1 1 map. So we finally proved that this I of A is an isomorphism of capital D with a subring of capital F. So this shows that capital D is contained in capital F. So far we have proved that any integral domain capital D can be embedded in a field such that every element of capital F can be expressed as a quotient of two elements of capital D. And such a field capital F is the field of quotients of capital D. And for that we defined using equivalent classes the elements of capital F, and we defined the binary operations and we proved that they are well defined, and we proved that capital F is a field under those operations. In the last lemma we proved that capital D is contained in capital F using the map I. Now in the next theorem we will show that every field containing capital D contains a subfield which is a field of quotients of capital D, and that any two fields of quotients of capital D are isomorphic. Now this is the uniqueness theorem. So let capital F be a field of quotients of capital D. So we have the field capital F and capital D, which is the integral domain, and it is contained in capital F. And let L be any field containing capital D. So we have L and D available to us. Then we need to prove that there is a map psi from capital F to L that gives an isomorphism of F with a subfield of capital L such that psi of A is taken to A for every element A in D. So we can see that any element in capital F is a quotient of two elements A and B in D, and the same set of elements are available in L also. So let us start with defining psi to be the identity map from capital D to capital D. That is, A is taken to A and B is taken to B under this map, which means that in L you can denote A with the psi of A and B with the psi of B. Now we can extend this map from capital F to capital L defined by psi from F to L, where any element in capital F which is of the form A over B, if I denote it as the quotient of A and B, and then psi of A over B is equal to psi of A or psi of B. Just in order to distinguish between the quotient in capital F and quotient in capital L, we write A over B F to identify a quotient in capital F and the other one with the L. So we make the corresponding changes in the definition of psi. Now we need to prove 4 claims related with the psi. So we need to prove that psi is an isomorphism. So what are the things that we need to prove? We first prove that the definition of psi makes sense. And the second one is that we need to prove that psi is well defined. And the third one, we need to prove that psi is a ring homomorphism. We need to prove that psi is a 1-1 map. And we don't need to prove that psi is an onto map, since we just need to prove that psi is an isomorphism to a subfield of capital F. So we go to the first one. So we need to prove that the definition of psi is sensible, that since we have A over B implies that B is not equal to 0, psi of B which is equal to B is also not equal to 0, and hence the quotient of psi of A or psi of B is well defined. So the definition of psi makes sense, which takes a quotient in F to a quotient in capital L. Next we need to prove that psi is well defined. That is, if there is another element in capital F which is equal to A over B, then let it be C over D. Then you can say that C over D is taken to psi of C over psi of D. And since C over D is equal to A over B, then we must prove that these two quotients, that is psi of A over psi of B, is equal to psi of C over psi of D. So we start with assuming that A over B equal to C over D. So by definition, this implies that AD equal to BC. Now since AD equal to BC, by applying the identity map, you can see that it is psi of A into psi of D equal to psi of B into psi of C, and hence we have psi of A over psi of B in L, and psi of C over psi of D in L must be the same. So we proved that equal elements in capital F is taken to equal elements in capital L. Next we are going to prove that psi is a ring homomorphism. So in order to prove that psi is a ring homomorphism, in general we need psi of A plus B equal to psi of A plus psi of B. So being we know the notations of the elements in capital F, we need to prove that psi of A plus B plus C by D equal to psi of A plus B plus psi of C by D. And this follows since psi is an identity map in D, since you can replace A over B with the psi of A over B. Similarly, you can prove the next property that is required for ring homomorphism, that is psi of A over B into C over D. Now by definition it is A over B into C over D, which is equal to psi of A over B into psi of C over D, since psi is an identity map in capital D. So we proved that psi is a ring homomorphism. Finally, we need to prove that psi is a 1-1 map. Here we can see that we just need to go through the steps of the proof that we used to prove that psi is well defined, but in the reverse order. That is, we start with if psi of A over psi of B equal to psi of C over psi of D, then A over B and C over D must be the same. Even though you start with assuming that if psi of A over B equal to psi of A over C over D, you will be going through the corresponding steps. So that is given to you as an exercise. So do the problem. Now we can see that the corresponding images of elements of capital F, that is the images of capital F under psi, forms the quotient, the field of quotients of capital D, which is going to be a subfield of capital L. That is, we are going to see it as a corollary. Every field capital L containing an integral domain capital D contains a field of quotients of capital D. So that follows from the previous theorem. And another thing that you can see is that any two fields of quotients of an integral domain capital D are isomorphic. That is also a corollary. And in the previous theorem, you can identify that this case appears when psi of psi, the map psi is onto. That is, when L is a field of quotients of capital D and every element is a quotient, where quotient of two elements in capital D, then you can see that L becomes psi of capital F, and we have the corresponding proof. Finally, you have two more problems to do. The first one is that you have given an integral domain. Capital D is the collection of all n plus mi, where n and m are integers. We call it the collection of all Gaussian integers. So you need to find or describe the field capital F of quotients of the integral, the given integral domain. So describe means you need to give the elements of capital C that forms the field of quotients of capital D in C. Similarly, another integral domain capital D is equal to the collection of all n plus m root 2 is given, where n and m are integers. So you can finally prove that the first one, the answer of the first one is of the form collection of all q1 plus iq2, where q1 and q2 are rational numbers. Similarly, the second one is the collection of all q1 plus root 2 q2, where q1 q2 are rational numbers. So you are requested to go through the proof and submit the answers in the Google Classroom. Thank you.